Thanks for watching AI Weekly Update from Henry AI Labs. We'll start off this weekly update with the exciting news of AlphaFold 2 from DeepMind. We'll look at what the protein structure problem is and some of the latest advancements, like the use of how they integrate the multiple sequence alignment features and how they build up this spatial graph using an attention operation. Inspired by the theme of the intersection of deep learning and biology, chemistry, or biochemistry, life sciences more generally, we'll also look at this paper, MolecularBERT. They show how you can convert chemicals into a string using this SMILE syntax and then process it in a similar way as the BERT model processes language, doing things like mass language modeling or a semantic pairwise similarity task to learn representations of these chemicals in the SMILE's encoding language. Then we'll look at a really interesting argument for scaling down deep learning and some of the utility that can be found, like exploring lottery tickets, the deep double descent phenomena, or meta-learning with outer inner loop gradients that can be best tested out with small-scale datasets like the newly constructed MNIST 1D dataset. Then we'll explore this talk from Yoshua Bengio on what causal inference, or this causal machine learning field, can bring to deep learning and how causal reasoning over events in a factor graph can enable flexible out-of-distribution generalization. Following this discussion on the intersection between causal machine learning and out-of-distribution generalization, we'll look at this paper on inductive biases for deep learning of higher-level cognition, getting back into this idea of what kind of inductive biases for our deep learning systems can be inspired from thinking about the difference between System 1 and System 2 thinking, or human conscious processing. So further on the topic of generalization, we'll look at this paper titled Generalization and Reinforcement Learning by Soft Data Augmentation, that looks at decoupling the use of data augmentation in policy learning and then auxiliary representation learning tasks. And it's an interesting overall view on how we're using data augmentation to learn representations in reinforcement learning. Then we'll look at this blog post from Google's AI blog on the vision transformer. It's a great animation that really describes quickly how they're processing these images with a vision transformer and how they've adapted this problem so that image grids can be encoded in the same kind of sequence modeling framework that's used for natural language processing. Then we'll look at this great talk from the NeurIPS conference that's currently underway. This talk was published yesterday, as of the recording of this video, about offline reinforced learning and this storytelling of how they built this QT-op dataset, which is like this robot arm farm, and they collect 580,000 of these interactions and really explore this problem of data-driven reinforcement learning. Then we'll look at Facebook AI's Rebel system. In this blog post, they discuss some of the limitations of mu0 or reinforcement learning with planning search algorithms on imperfect information games like poker compared to, say, chess or Go. Then we'll look at some recommendations from the HuggingFace science team from the EMNLP conference. And this is really great because there are tons of these papers that have been published in this top conference. And so it's great anytime you can have some kind of curation of what's worth reading. And then finally, we'll look at this really great implementation of supervised contrastive learning. And I really want to highlight how interesting it is that this paper is, pretty cutting edge. This is supervised contrastive learning, and it's moving quicker into this collection of Keras examples. You can run it in the Collab notebooks, and it looks like it's getting easier to take these latest algorithms and start to build code and integrate it into whatever problem you might be working on. The big news in deep learning this week has undeniably been the release of AlphaFold 2 from DeepMind that competed in the CASP-14 competition. CASP-14 stands for the Critical Assessment of Protein Structure Prediction, and this is the 14th such competition. So DeepMind previously had AlphaFold 1 compete in CASP-13, and this is the CASP-14 competition. So this graph shows the massive improvement that was achieved by AlphaFold 2 compared to every other competition that tried to predict this three-dimensional protein structure from the amino acid sequence. So what the competition is you have these new set of amino acid sequences that have just been experimentally verified. So they have these techniques like the nuclear magnetic resonance imaging, cryo-electron microscopy, or the X-ray crystallography that they use to completely determine the three-dimensional structure. And this is how they get the ground truth labeling for these data sets. So what does this data set look like? It's a data set in the protein data bank where they have about 170,000. They describe it towards the end of the paper, or the end of the blog post, where they have about 170,000 of these protein structures from this protein data bank. So they have 170,000 of these one-dimensional amino acid sequences that have been experimentally verified with things like the electron microscopy or any of this kind of stuff that I have no knowledge in. But these are kind of the ways that they get these ground truth three-dimensional structures from the corresponding one-dimensional amino acid sequences. So in the blog post, they recommend checking out this video from the Protein Data Bank YouTube channel about what is a protein and helping you get familiar with this problem if you have zero sense of biology and only have a background in machine learning or deep learning. So they basically are presenting how protein structure is formed by the folding of these chains of amino acids, how the shape of a protein is what determines its structure, and then kind of talking about why it's interesting to know what the shape of the protein is. And they talk about things like how the shape of hemoglobin allows it to carry oxygen or things like this, that the specific biology of how this is important. So they haven't provided a complete explanation of exactly how AlphaFold 2 works, although there is a full paper on how AlphaFold 1 works. But you can kind of gather from this blog post and this diagram a rough sense of how it works. They also have an abstract submitted in the CASP14 journal where they describe a bit about what the system is. So there are kind of, I think, two parts worth discussing. So the first of which is multiple sequence alignment. So if you take in a bioinformatics class, they start you off by teaching you how to use dynamic programming to try to find the similarity between a bunch of different amino acid sequences. So you line them up and then you have a similarity score, and then you use these similar sequences to try to infer properties about the new sequence, because the whole idea of this is that the sequence of amino acids should be able to determine the structure. So the nearest neighbor sequences are going to be highly informative. So in this way, it's kind of like an information retrieval problem where you might have these nearest neighbors. So it's kind of similar to how like the retrieval augmented generation model, if it goes and retrieves similar articles from Wikipedia, it helps it make its latest inference. And it's kind of like that. You're trying to find these nearest neighbor amino acid sequences, which you do have these verified structures for, so they make for really good features to integrate into the model as it's predicting this new sequence. So then the second part of this is kind of how it's developing this three-dimensional structure of the protein. So I made a quick video about this idea that if you had this three-dimensional structure represented in a cube, so you have this dense data structure where you have height by width by depth, then you're going to have a lot of values in that cube, and trying to do something like a 3 by 3 by 3 convolution would be really computationally expensive. So instead what they use is they have a sparse representation where you use the transformer, the attention neural network, that can take advantage of having a sparsely occupied amino acids within this three-dimensional structure. So you see how if you imagine putting a cube around this kind of this shape example, and you see how you have the different structures, and if you put this, say this is like an amino acid residue, this kind of part is like the side chain, it occupies a small set in the overall cube that would take up this whole the space that would occupy this data. So they talk about how they have this intermediate step of building up this sparse graph in this way of having the topological connections with the transformer networks, and then integrating the features from the multiple sequence alignment embedded features as well. So I thought another interesting detail of this is how much compute is being used for AlphaFold 2, because you might imagine that it's some massive amount of GPUs that are used on this, but they describe how it's about 16 TPU v3s, and it's equivalent to about 100 to 200 GPUs run over a few weeks. So that's really not so bad compute-wise, what you might expect from some latest model from DeepMind that achieves some breakthrough performance. So all in all, hopefully this quick idea of the multiple sequence alignment and how they have these nearest neighbor-like features that are embedded into probably the intermediate layers of building up this 3D graph, and then this 3D graph of the protein structures is probably being done with like a sparse attention mechanism, and it's probably represented with the edges somehow, maybe in like a graph structure, but probably it can just be in like a matrix format, and you just use the attention operation rather than having to have like a graph convolutional neural network where you're explicitly representing it as nodes and edges. But maybe it is that, I'm really not sure. So with respect to how this really changes everything, I'm not an expert on that and I'm not sure exactly, but I have read some of these papers about how they applied AlphaFold 1 to predict the spike shell proteins on SARS-CoV-2 virus, and reading a bit about how well they were able to so the idea of this would be the cryo-electron microscopy, one, it's expensive, and then two, it takes a while, compared to this AlphaFold 2 thing where you just get the the RNA sequence, and then you can derive the amino acid chain from that, and then you could have the a guess on the protein structure for these virus shell proteins, like just as quick as running a forward pass of a neural network, compared to the cryo-electron microscopy. So I think one final thing that's really interesting about the protein structure prediction thing is that they have 180 million protein sequences in this universal protein database UniProt compared to the 170K verified structure. So it's kind of this interesting semi-supervised problem that maybe could be explored further. So really quickly, I wanted to credit this great article from a PhD student in the Oxford Protein Informatics group who attended the competition and really goes into more detail about what is AlphaFold 2, what is protein structure prediction, and how does this compare to other approaches, and how will this change things. So this is a really great article. I also enjoyed videos from Yannick Kilcher and Lex Fridman on the topic as well. So like many of you, I imagine, the results from AlphaFold 2 really sparked my interest to look further into areas of where there's an intersection between deep learning and then, say, biology or biochemistry. So this paper is titled MolecularBERT, and the title is Molecular Representation Learning with Language Models and Domain-Relevant Auxiliary Tasks. So to begin with how this data is represented, they take these chemicals and they turn them into strings by using this SMILES language. So this SMILES way of processing a chemical language system was developed in 1987, and it has this special syntax where you use the parentheses and things like this to try to encode this graph structure of chemicals into kind of this like sequence of tokens representation that is a perfect fit for, say, the BERT model. So one thing that, and then another thing is kind of the task. So they talk about virtual screening and then QSAR, which is quantitative structure activity relationship modeling. So these are two of these, like these molecular tasks. And they have another paper titled MoleculeNet, not from these same authors, but they are basing it off of this MoleculeNet, which is a data set of these different tasks. And I know nothing about this, but what I thought is interesting is the way that the BERT model is so well fitted for any of these kinds of problems, this kind of framework of self-supervised learning as well. So they have this SMILES representation where they have this discrete tokens, and it looks like, any of these natural language processing problems. And they do mass language modeling where, say, you would mask out like the carbon spot or the parentheses spot, this kind of thing where you just mask out and reconstruct this discrete sequence of tokens and then use it to learn representations. And they also use like a similar idea of the next sentence prediction task or any of these pairwise similarity tasks that BERT has been so good at, like, say, the Quora question pair similarity detection, or things like, are these semantically equivalent? They use that by passing in two different SMILE encodings of different chemicals, and then they tell if they're similar or not, because apparently there are many ways to encode a SMILE string that is an equivalent resulting shape depending on how you traverse the graph. But all in all, I just thought the takeaway was really interesting to see how data can be formatted for the BERT model and how it can take on these different kinds of tasks. Scaling down deep learning is another really great paper that came out this week. This paper is arguing for developing more around small-scale experimentation in deep learning to complement the large-scale scaling up of models like GPT-3 with 175 billion parameters, or say like the T5 model with 10 billion parameters. So they compare the exploration of deep learning with the Human Genome Project and how they experimented on fruit flies to have this complement of small scale and large scale, and using this analogy throughout the paper to illustrate why we should do this small scale experimentation with, say, the MNIST dataset, or they even propose the MNIST one-dimensional dataset as an even smaller version of MNIST to allow for faster iteration. So before further describing the differences between the new MNIST 1D dataset that's proposed in this paper and the original MNIST dataset, let's jump right into some research areas of deep learning that would benefit from this small-scale experimentation. So they also have a blog post on this that is nice to read as well. So the first of which is finding lottery tickets. So the lottery ticket hypothesis has been one of the most popular papers in deep learning. And the reason it's interesting is because we've seen how we can prune these deep neural networks. We train a model like BERT, and then we mask out most of the weights to zero, and somehow it can still retain the same performance as the original model. And this is used for compression because you mask out the weights, and then you throw them away, and then you have a much smaller file size to hold the weights of the model. But it would be really interesting if we didn't have to first train all the weights and then prune them. We'd rather be able to somehow train the sparse subnetwork right from the beginning. And the lottery ticket hypothesis shows that this looks like it's possible to do. They have this iterative magnitude pruning thing where they, rewind, reset the initialization, rewind, reset the initialization. And that's how they show that you could train the sparse subnetwork from scratch, but it's not exactly how to do it. You still do have to train the full thing with the original lottery ticket hypothesis paper. So they're still kind of looking at how we can train these sparse subnetworks right from the beginning, which would make it much more computationally efficient to train these deep neural networks. So the second example of a use case for this smaller scale experimentation with the MNIST 1D dataset is to learn more about this deep double descent phenomena. So this paper, Deep Double Descent, it shows that models have this threshold where it looks like they've overfitted, but then suddenly they hit this interpolation threshold and then they start to generalize even better. So it's like a bizarre phenomena that's not really understood that well, is how this deep double descent thing occurs. And the next thing is gradient-based meta-learning. So this has been, there's a whole course on Stanford on this, taught by Chelsea Finn, about how you would use these inner-outer loop gradients where you have like a teacher and a student, and then gradients flow from the student to the teacher, and the teacher can control all these crazy things like the initialization of the student network, say the label distribution where you have things like pseudo-label smoothing. And there's another paper from researchers like Jeff Clune called Generative Teaching Networks, where they even have the teacher generate the data set for the student network. So this is another idea where doing large-scale experimentation with gradient-based inner-outer loop optimization is really computationally expensive for large-scale datasets. So now that we've motivated the need for small-scale experiments to explore lottery tickets, do the deep double descent exploration, or explore this idea of inner-outer loop gradient optimization, let's talk about why they propose MNIST 1D and why they say the original MNIST dataset isn't really good enough for this small-scale experimentation. So the first problem they state is that the problem with MNIST is that logistic regression, multi-layer perceptron, and convolutional nets, they all basically completely solve the problem of MNIST. So you can't really measure the contribution of, say, the spatial priors in a convolutional layer because they all completely solve the handwritten digit classification task. So the second problem they state is that it's a pretty big data set for a toy data set. So MNIST, it's height by width, grayscale images, but it's still 28 by 28. And if you flatten that out into a vector, it's a 784 dimensional vector. So it takes a little bit of computation to do MNIST classification and just loading and processing the data for the sake of things like, like GANs or generative teaching networks for mentioned before. It's a bit of a large data set for those kinds of explorations. And the third problem is that MNIST is hard to hack. And by this, they mean it's not procedurally generated. So there's some procedurally generated environments that have been built for reinforcement learning where, say, you control these parameters really easily because these environments that you test out things like bipedal walking agents, you render the environments based on some parameters, and it's easy to control, say, the hilliness of the landscape the agent's going to walk on, or the depth of the ditches, these kind of things, and that makes it procedurally generated. So to solve this problem, they flatten the MNIST into a one-dimensional sequence where, say, the digit 3 would be represented by 1, 2, 3, 2, 1, 2, 3, 2, 1. So that kind of draws out like a 3. So they have this kind of way of representing the data, and that makes it 20 times smaller and easier to test out things like the translational invariance, inductive bias. One of the fastest rising, most interesting areas of deep learning research is the intersection of causality or causal inference and machine learning, also called causal machine learning. So this has probably been mostly campaigned by The Book of Why from Judea Pearl. And this book talks about the importance of being able to explain, what causes things and problems with only correlations and only looking for correlations in the data rather than constructing causal models. This course from Brady Neal on YouTube, this whole thing is linked in the description of this video. It's really like the best course I've seen out there to get up to speed with causality, explaining things like the Simpsons paradox and what is there to causality that's different from what you might have been studying with machine learning. So this talk from Yoshua Bengio is talking about what causality brings to the table of deep learning research. And it's such an interesting talk. It's an hour, 30 minutes. So there's a lot to this, but I'll try to just quickly give like 3 slides that I thought were really interesting. So right off the bat, he talks about how the people who've been using causal inference are mostly social scientists or medical scientists who are trying to answer questions like, does smoking cause cancer? Not thinking about how does a baby come to represent the world, like in the sense that we think about, say, model-based reinforcement learning, or these kinds of questions that deep learning researchers are thinking about. There hasn't really been this intersection between the two ways of doing this kind of, I guess, like statistical modeling. So he starts off right away by describing what is missing, what is the difference between our deep learning systems and then human intelligence. And he says one of the most important things is flexible out of distribution generalization. So already tons of these papers are taking apart how, this idea of the train test split as a way of evaluating models is kind of insufficient, and we need different ways to evaluate generalization. So the idea is that out of distribution generalization and having this kind of flexibility comes from this compositionality of representations, or having some kind of, say, disentangled representation or a sparse factor graph where you can recombine existing concepts into never seen before examples like science fiction, or in this example, constructing this kind of new vehicle from these previously seen vehicles. So it's presenting how compositionality and how we have these several layers of processing in deep neural, the sequential processing that starts off with, say, the edges and then forms eyes and noses and then recognizes whole faces, how this compositionality is one such example of like a prior kind of something built into the structure of a deep neural network that helps it do this kind of flexible generalization and recombination of abstract concepts. So I'm going to jump around a bit and probably lose a lot of the story, but the high-level idea is that it's following along this inquiry about System 1 and System 2 thinking. So there's this famous book from Daniel Kahneman, Thinking Fast and Slow, that inspired the deep learning research community to think about System 1 deep learning compared to System 2 deep learning. And the best example of this, in my opinion, is, say, the mu0 algorithm. It has System 1 mappings where it takes a state and then it just produces an action with this distilled policy. So that's kind of System 1 intuition thinking, where you just do this quick mapping from state to action. And then you also have in mu0 this Monte Carlo tree search planning. So planning algorithms using your world model and your intuition to guide thinking ahead these different trajectories, and then using that kind of symbolic planning to make the best action. That's the System 2 thinking part of mu0. So it has the System 1 intuition and then the System 2 planning. So the idea then, with respect to this idea of how does causality bring about flexible out of distribution generalization, is that there may be some inductive priors that we can derive from human conscious processing or planning, this kind of conscious thinking, whatever that means. And he also relates it back to, say, verbalizable and non-verbalizable knowledge. A lot of different ideas are in the air with this. It's an hour 30 talk, but to just distill it massively, it's looking for inductive priors in conscious processing that might help us discover how to do this. So the idea again is sparse factor graphs, where we have, these relations that involve a very small amount of all the variables that we know about, like the hand drops the tennis ball. We know about all sorts of other things as well, and it makes a very sparse set of our variables in our representation. So then finally bringing it out, the causality part is how we have these causal reasonings over these factor graphs, which is how we take advantage of them to do this kind of out of distribution generalization. In addition to Bengio's talk in Brady Neal's Causal Inference channel, Bengio and Goyal have published this paper, Inductive Biases for Deep Learning of Higher Level Cognition. So all in all, there are a ton of ideas in the air, but let's take apart this idea of what is an inductive bias or prior in these deep learning systems. So this table is a list of different inductive biases and the property that they result in. So we have things like convolutions and convolutional neural networks, and the corresponding property is the group equivariance, or having this kind of spatial symmetry as you're sliding these filters across the images. So these are these different biases that we use in our deep neural networks, and this is the property that they correspond with. So say compositionality is the property that we're after. The prior that we would look for is this sequential processing of the deep neural network, and it has this composition of layer 2's features into layer 3, 4, 5, and so on. So that's how you produce compositionality from this bias of the deep sequential architectures. So another concept in the talk is how these attention layers bring about these sparse factor graphs, because attention is this operation where you apply this softmax to the query key matrix multiplication that basically makes the large values super large and the small values super small, such that you have this kind of sparse activation, and that's how it attends or selectively looks at a small part of the input given a massive set of inputs. So it's one example of an inductive bias that produces this corresponding property. So just, there's so many ideas in this paper and the talk, but what are the inductive biases that we might be able to derive from thinking about conscious thinking? Data augmentation has been a super useful tool in deep learning to prevent overfitting, or also I think induce these inductive biases, like you should be invariant to rotating objects or translated objects, or even playing with the color or the texture and still recognize the semantics of this object. So data augmentation is having all this utility for developing these deep learning models, and it's also used heavily in reinforcement learning. So one example of how data augmentation is used in reinforcement learning is in OpenAI's paper, Solving a Rubik's Cube with a Robotic Hand. The way that they do that is they have this algorithm called automatic domain randomization, where they have a procedurally generated environment where you can control the parameters of the physics simulation as well as the visual information like the lighting or different characteristics like that. And they have this curriculum of sampling from this data and permuting the data such that when the robotic hand gets to the real world, it has seen such a diverse set of landscapes that it just generalizes to this new configuration of lighting and physics. So in this paper, they're looking at this idea of having auxiliary representation learning as well as learning a policy for a control task. So another famous paper like this is titled Curl from researchers at UC Berkeley, where they simultaneously do contrastive self-supervised learning with the data that's collected by some kind of vision-based robotic system, as well as learning the policy. So they have this loss function on the representation that's used for contrastive self-supervised learning and for policy mapping. So in this paper, they're arguing to separate out the data augmentation used in the auxiliary task with the policy task, because they argue that learning the policy is hard enough as it is. Don't add data augmentation to that part, just add data augmentation to the auxiliary representation learning task. Also new in AI this week, Google has published a blog post explaining their vision transformer model. So this is their experiments on adapting the transformer neural network for image classification compared to, say, using the popular convolutional neural network. So the idea of the vision transformer is to start off with an original image and then slice it into patches and construct a grid of the original image. So then you have these 16 by 16 patches from the original image, and you flatten that into, say, a 256 dimensional vector. Then you pass that vector into a feed-forward layer that compresses the dimension of the vector. So say you pass in a 256 dimension vector that corresponds to this patch in the original image, and then out comes, say, a 32 dimensional vector that's much smaller for the sake of passing it into this attention layer. So then you concatenate all of the compressed vectors from each of the original patches. You add in the learnable embedding for the position in the original image. So this kind of learnable embedding, it's used in sequences to denote, the transformer attention layer is a set operation that has no understanding of, what order of the sequence the different elements are in. So you add in this learnable embedding to give it the notion of, this token was the first sentence in the first word in the sentence. This was the fifth word in the sentence, and so on. So they're using this learnable embedding to signal to the visual transformer which section of the original image this particular patch came from. So then this concatenated set of vectors and their added embedding is passed into one of these attention layers, and then it has the same kind of transformer architecture, just with the same kind of matrix input where you still have the projection of the query key value matrices and do the attention operation. And then you slice it as in the BERT CLS token idea and classify the ImageNet style. So this is a really nice animation for getting a sense of how they've adapted the transformer for image classification. The NeurIPS conference, one of the top conferences in artificial intelligence or deep learning, is currently underway, and a lot of these talks will be posted on slideslive.com. So here's a talk on offline reinforcement learning, from algorithms to practical challenges. So if you're not familiar with offline reinforcement learning, the idea is how can we do reinforcement learning with previously collected data? So building large data sets for doing reinforcement learning. And the reason why this is so different from, say, supervised learning is in reinforcement learning, you're updating this policy that's used to sample the data. So say you sample some data, then you do some reinforcement learning, and then you have this new policy. The new policy will then cause you to make much different state to action decisions that will take you on these totally different trajectories from, say, what you might have sampled with a randomly initialized policy or a policy from, like 10 updates ago. So offline reinforcement learning, also known as batch reinforcement learning or data-driven reinforcement learning, is how can we do reinforcement learning with these large previously collected data sets without sampling data with the policy that's being learned. And one application of this that I think is just extremely interesting is doing treatment control with doctors in hospitals. So you make this decision from a patient's state into say a medical action or a lab test or a surgery. These are the kind of action decisions that are being made based on the patient's state. So say we wanted to use a deep learning doctor. We can't just deploy a random policy. It has to be able to learn from these existing data sets of what's been prescribed by doctors and learn how to sample out the good and the bad and all this different stuff that we might be expecting data-driven offline reinforcement learning to be able to do. So this is a really great talk. This is the table of contents of the talk, starting off with what is reinforcement learning, what is offline reinforcement learning, why is it uniquely different, ideas like the importance sampling algorithm, these fundamental ideas. So to maybe sell you on watching this presentation a little more, I really like the storytelling of this offline reinforcement learning series of experiments from these researchers at, I think, UC Berkeley is where they're doing these experiments. So they describe their QT opt paper, and as you can see in this image, they have this like row of robotic arms, like a farm of robotic arms they use to collect an enormous data set of 580,000 interactions, these state action next state transitions, or at least I think that's how they're recording each individual interaction that makes up the cardinality of 580,000 such interactions. But so it's really interesting because they describe how they set this up, collect this massive data set, and then from building such a great data set, they can see and disentangle the challenge of offline reinforcement learning from a data problem or an algorithms problem. And with having such a great data set, they're able to say that, this is an algorithms problem. And then the storytelling of this presentation goes on to talk about the sequence of trying different things and making this work with, building on importance sampling and all these other interesting ideas. So I highly recommend this. It has a great storytelling of their process of digging into this idea of offline reinforcement learning. Facebook AI has recently published about their Rebel system, a general game-playing AI bot that excels at poker and more. So the blog post begins by describing these imperfect information games like poker and how that's different from something like chess that MuZero is really great at. So chess, you see the board, you have all the information, compared to poker where your player has a hidden card and you don't know what that hidden card is, and thus it's an imperfect information game. You don't have all the information that you would need to make your optimal actions. And then there's another part of this where you need to have a sense of your opponent's strategy. So MuZero, and I think the whole chain of AlphaGo, AlphaGo Zero, AlphaZero, they're trained with some kind of self-training where they play against copies of themselves. And these games like chess and Go, they don't really require having like this unique model of your opponent, because your opponent can't play like some crazy unique strategy in chess that kind of like is super adversarial to your policy, or maybe it is. But so this idea is there's this competition on Kaggle right now, which is rock, paper, scissors. And if your opponent is just playing the Nash equilibrium and randomly sampling rock, paper, scissors, I don't think there's really anything else you can do. But if your opponent, say, only samples rock, well, you got to adapt to that and then only play paper to beat them. So the idea here is transitioning to having belief states about what kind of policy your opponent is trying to use. And they adopt this for rock, paper, scissors, and then they talk about this modification to poker. So here's the modification to the poker game that they're exploring. And I can't really interpret this much more for you. I don't know much game theory, just going to present this and then let you decide if you're interested in looking into this further. So instead of both players having a hidden card and then making decisions based on that, both players are going to submit their policy, and then using the referee, which will interpret the decisions based on the policies that have been submitted, you construct a belief about the card the other player has. So in this way, they talk about how this changes the game from imperfect information into a continuous state, perfect information game. In last week's AI Weekly Update video, we went through some of the papers that were awarded Best Paper Awards at the EMNLP 2020 conference. So all in all, there's probably like somewhere between 300 or 500 of these papers that have been published in this top natural language processing conference, and it can be really hard to try to take apart which ones are worth reading. So here's a really great curation from the HuggingFace science team, some of the titles of papers from this conference, and then a short, usually 2-sentence description of why the member of the HuggingFace team chose this paper to read further. We've seen a ton of success from self-supervised contrastive learning like SimCLR, MoCo, Bootstrap Your Own Latent, Suave Unlane Clustering, and then most recently, just a simple Siamese representation learning framework. But contrastive learning has also been really useful in supervised contrastive learning. So the core difference here between supervised and self-supervised is that in supervised learning, the positive pairs are members of the same class, so say another dog image, rather than a data augmentation transformation of the original image, which is what's used in self-supervised learning. So I just wanted to point out that so they have this collection on Keras examples of implementing a lot of these papers, and there's a ton of great code examples on Keras examples in computer vision, natural language processing, and so on. So here's kind of the latest one that came out this week. It's an implementation of supervised contrastive learning that takes you through how to sample the pairs, construct the training loop, use the contrastive loss function, add the projection head to the embedding of the network, and just an end-to-end example of how to implement this, pretty cutting-edge technique in supervised learning.